Okay. So hello. So today I'll give brief. So we're essentially finalizing the course. So today I give a brief. So we passed through some of the questions which I tried to put more in the mathematical language of what we have in turbulence. So today I give you a short introduction to the one of the actually central questions in turbulence, which are, however, mathematically is very poorly understood. Is intermittency. You already had it in lectures of Simon, so I briefly recall what is it all about, and then I will not give you I'll give a very brief idea of the existing views of what is intermittency, and then it will just give you one explicit example where intermittency can be studied and seen rigorously. But this is a recent work of the last year. So so intermittency has to do with the dependence of velocity fluctuations which we call delta UL on scale L. So delta UL is a velocity fluctuation on scale L, and what it means, so usually in fluid dynamics, for example, what people like to use is fluctuation is a difference between velocity at, so you take a point R and then you put a vector in direction E to the point R plus LE. Right? So it's 2 points which are placed at a distance L. So we take a difference between velocities and usually the typical quantity that you project it on the direction. Take a modulus. So this is what's called longitudinal fluctuation of the velocity at distance L. So the distance or difference of the velocity at 2 points at distance L projected on that direction. But there are also many other concepts. So what we do? What is intermittency? So the observation, which comes both from experiment and numerical analysis, but not yet from a theory, is that for large Reynolds numbers, for very large these numbers. So in that limit, when we get developed turbulence, so there exists what's called inertial interval of scales. So this interval of scales is between the big L and small eta. So the big L is force. It's usually called forcing scale. So if you remember this video with a cup of coffee, that this will be scale size of the cup. right? So this scale at which you usually force, then the scales we want to consider is a small scale. So the small details of the motion, which is much smaller. But then it turns out that when you consider small and small scales, at a certain moment there is what's called Kolmogorov scale. Or viscous scale. So it's sufficiently small scale. Fluid is viscous, so at certain small scale, the motion is start to be influenced by viscosity. So it does not evolve anymore in a turbulent way. Okay, so this is assumption, and usually it's assumed that this viscous scale goes to 0 as Reynolds goes to infinity. Yeah? So essentially, when in the limit for developed turbulence, this interval becomes, let's say, very large. So it becomes it corresponds to all scales which are smaller than the scale of the whole problem. So up to very, very, very small scales. So in this interval, in this interval, so clearly that at the scale L capital, everything is very non-universal. It depends on how you change this, how you force the system. So if you use big spoon or small spoon in a cup of coffee, everything will depend on it. But it turned out that at smaller scales, everything becomes universal, and universal in a special way. So in this interval, we have what's called structure function. So it's structure function. And structure function is defined as average of this structure function of order p, so a different order. Usually p is positive integer number. And it's defined as the average of the velocity fluctuation in the power p. So you see this average is usually space or time. So it's either space or time average. Usually doesn't matter. So you just take mean fluctuation in the power p, and this is called structure function. So it's proportional. So this is called proportional. So this sign means that it's equality up to a coefficient. To L in certain power zeta p. For some power zeta p. So this is quite a universal behavior because it's power law. So we have all structure functions behave as they change with the scale as a power law. And this is interesting fact. So it's interesting. Fact. So the question why does it happen? So why? So first of all, in order to understand, in principle, not only why it happened, because why it happened is still open question for fluid dynamics, but rather what it means, what this power law in principle implies. Let us discuss equations of motion. So what are the equations of motion which are governing these quantities? And what we can see is that there are two things. So first of all is L is much smaller than L capital, which means that for these scales, we can neglect effect of forcing or boundary conditions, which is in that sense the same thing. So the scales are much smaller than the, for example, imagine that you have a cup of coffee. Cup of coffee, and it has a size L. So we want to know what happens at small scale, small L, which is small but not too small, because but it's anyway it's much smaller than L capital. So in that case, usually these points are far away from a boundary, and in principle, so it's reasonable to neglect effect of forcing at that scale. And another property which is usually assumed is that L is much bigger than viscous scale, which means that we can neglect viscosity. I can neglect viscosity. So which just leave us as equation of motion, the Euler equations. Euler equations. So we already discussed a lot that the meaning of Euler equations is very unclear. So in which sense they give a solution of turbulence, but at the same time, we can assume opposite, that the solution at least satisfies these equations. So let's remember what is Euler equations. Okay. So since we have this equation, we can discuss what are the symmetries of this equation, and then connect symmetries of this equation with the power law for the structure functions. So we have scaling symmetries. Of Euler equation. So there is a class of symmetries that we discussed several times. So it's a symmetry which maps time, coordinate, and speed into alpha times 1 minus h time. So it stretches the time or compresses the time. Also, it does the same with the scale, but with a different power. And with a different power, it transforms velocity. So this transformation maps solution of Euler equation to another solution of Euler equation. So it's still solution for any alpha positive and h real. So h is will be exponent of our scaling law. You see, so h defines the difference of how much you. So when h is 0, you scale time and space in the same way. Where h is not 0, it means that you scale time and space differently. Good. So what you can see that if solution is self-similar, for some h, what means self-similar? That means that whenever you make this transformation for some given fixed h, you get exactly the same solution, at least statistically. So it means that you don't need to get exactly the same solution, but at least it's the same in the sense that statistical averages will be will be the same. Then automatically you can compute zeta p. Then what? Then whenever you change scale, you change u in the power h, right? So if L changes by 2, then u changes by 2 power h. So automatically, up will change in u power ph, which means that the only power law that you can put here, which will be in agreement with the symmetry with given h, is L zeta p, where zeta p is h p, linear in p. So whatever, if you assume that whatever symmetry, so one of the symmetries is really respected by your solution, at least in statistical sense, then you immediately fix all these exponents. And in particular, this was exactly the Kolmogorov theory of turbulence. Kolmogorov theory from year 1941, where he argued that h should be 1/3. So it comes from energy conservation. But apparently this is not true. This is not true because observation, both numerical and experimental, clearly gives tell that zeta p is a nonlinear concave function of p. So what really happens is that if you put zeta p as a function of p, instead of being straight line, which give you k41, the true value is that this is function like this. 1, 2, 3, 4, and so on. So there are only 2 points when they intersect. So when the linear law of Kolmogorov intersects with true value is value 0. This is clear that if you put 0 here, it will be 1. So the power should be 0. So 0, 0 is a point. And then there is another point which is 1. At the third moment, this also has to do with energy conservation. So this we will not discuss today. But anyway, so the important is that we have nonlinear form, which means that the true turbulent dynamics is not compatible with any scaling law. So what we can say is that so the question we can put is how this is possible. No? How this is possible. So it means that nonlinearity of zeta p. So how at all you can create a vector field which is which has these power laws which are not compatible with any scaling law, and still it's a power law. So why power laws at all appear? Sorry. So there are 2 issues here. So the first is immediately that we just discussed is that all scaling laws are broken. All scaling symmetries broken. At the same time, there was a very successful idea which gave many conclusions which really in agreement with what we observe, but it's fully phenomenological. So it's the idea of the Paris friche. Which actually something like, you see, certainly this power nonlinearity of zeta p is not compatible with any of the power law, with any of the scaling law. But if you fix p, consider the corresponding zeta p, then it is compatible with certain h for the given p. But this will be different h for different p's. So the idea is that, okay, all scaling symmetries are broken, but somehow all of them are restored, just not everywhere. In some place there is one symmetry restored, in another place another symmetry restored. In third place, another h is restored. So somehow this all family of symmetries somehow restored in some entangled way, in such a way that each structure function is influenced by proper h in some way. So actually, idea is I'll just write the quotation. So what they say is that singularities of arbitrary exponents which means arbitrary h, and mixtures thereof are consistent with the equation. This is not a very mathematical statement, certainly, because equations are nonlinear. So what means singularity? Singularity means that in some space, a part of the space, you have a flow which has a scaling with some fixed h. And whenever h is smaller than 1, it's a singularity. You see, because it scales as singularly. The flow is not differentiable. So for example, given one h1, you have some flow when you go into smaller scales, you have a certain singularity. In some part of the flow, you have a certain scaling of the velocities as you go to smaller scales. But in another place, you have maybe something different, so some h2. And you have some spread difference, some collection of singularities. Each one has its own h, so somehow they can influence differently these power laws. And there is so Paris friche gave this direct way how the h and how the singularities can be connected with zeta p. At the same time, this is certainly not far from being any rigorous statement, because you cannot say that arbitrary mixture of singularities is consistent with the equation, because the equation is nonlinear. So the sum of the solution is not a solution. So that's just an image. But that's was very successful way how you see how you see the turbulent flow. So the turbulent flow should contain all kind of singularities with all kind of which scale with all kind of different age in different places of the space and time, and they mix in such complex way, so they give you this zeta p depending non-linearly on p, and this is exactly what means intermittency. So intermittency is a kind of mixture of different types of behavior. So here it's one behavior, then another behavior, another place, another. It's also not only in space but in time. So first it's some very intense oscillation, then it's become much less intense, then becomes intense again, then something in the middle. So it's exactly intermittency. So there is a very strong change from one type of the behavior to another type of behavior, both in space and time. So this is the image of what it should be, though we can't really go much longer than that. At the same time, there are ways how you at least construct artificially the fields which are intermittent. So there is a way how you can construct intermittent fields. Essentially, through this idea or through the idea of Markov process that Simon discussed. So what I wanted to give today, because it will be last lecture, so I want to give you one example when everything is solvable. So we take example where we do have this law and where we can exactly compute zeta p's. So exactly rigorously compute zeta p and then see what's the reason for this nonlinear dependence, which is usually called anomalous scaling. That's the question. So we just see how anomalous scaling develops in this specific example. So what I'm going to do, I want to explain my recent paper, so it will be solvable example. That's paper from last year in journal Communication with Mathematical Physics. Okay, so let's construct example where we can find solution, find structure functions, and compute exponents. So we will work. Certainly, we are not going to do anything like Euler equation, but we already learned that there are simpler models. So we will create a shell model. And recall what is shell model. So a shell model is a collection of variables, which are all complex. And n is 1, 2, 3, and so on. So n is positive integer. And to each n, we associate a scale. So this is scale. So we have sequence of scale, bigger the n, smaller the scale. So this is exactly going for 1, 2, 3, 4, 5, and so on. We go to smaller, 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 smaller scale. So this is how we model multi-scale process. And then what we will incorporate into this model is the symmetry. So we want to see the interplay between the symmetries and the intermittency. So we incorporate the symmetry. Scaling symmetry. So now, you see, you cannot just multiply the scale by any number because it's only power 2. So we can So what we can do is we can relate scale n plus m with the scale n. So whenever you move from one scale to another, they're related by a product, by a perfector. So we take alpha is 2 minus m. So this is analog of this relation between the for the space scaling, and then additionally we have to make connection of times and speeds. So we should, just like in that formula, we should put alpha 1 minus ht. So this is how we scale time. And how we scale velocity, it should be alpha hu. So we go from n to n plus m. So this is equal. So this will be the scaling symmetry. Again, it will be a family of scaling symmetries depending on this exponent h, which is analogous of the scaling symmetries of the Euler equations. With the difference just that alpha is not any number but just power of 2. But it's from qualitative point of view, this not very important. So this will be a family of symmetries that will be broken by intermittency. So this is what we want. So there is family of symmetries, just like in Euler, and here it's broken by intermittency, by the fact that zeta p is not linear. And here we also make it broken. And then, in order to see that they are broken, but at the same time there is a kind of Parisi-Frisch picture, is that is through the structure functions. Structure functions are defined so on these scales are defined as the average of un power p. And this is by definition temporal average. So we have no space in the usual form. So here we just take temporal average. So it's limit when time goes to zero to infinity of 1 over t, integral from 0 to t, un t p dt. So the mean value of the on long time. So the question is that what we want is that these structure functions will scale in some power zeta p for nonlinear zeta p. So this is the question. So this is what we want to construct. Okay, so I will write a model equations for the shell model. These explicit equations, they are a bit heavy, but this is because they are designed in a special way so that everything can be solved. So you see that equations are somewhat not so compact, but whenever we start solving it, everything will become simple and simple. So model equations. So the un, so we have to write equation for un, and it is kn. So let's define kn as 2 power n. So this is wave number. So inverse of the scale. So wave number is inverse of the scale. Un square Fn plus Un sum m smaller than n, real part Km Um star Fm. That's it. So this is a question. So we need to know what is F. So F, so where Fn is what? Fn is a certain ratio. So it's Un minus 1 square over Un modulus square by some function of complex number. Okay, and this function is also explicitly given. So for this function is, let me write it so it will fit. This is Fn, and now we have to define what is small f. Small f is a function of complex number, and it will be defined for one more function. So it's expressed for one more function. Like this. So which is just written in polar coordinates. So z is rho e I theta. So this is complex number written in polar coordinates, and then this function, this is the complex function which is described through this modulus phase, and R is any C2, so twice continuously differentiable positive real function of theta on a circle. It's modulo dash p. Circle modulo dash p. Okay. So that's a model, and in addition to the model, you see for the n equal 1, the question is that you will need u0 because of n minus 1. So we need to add one boundary condition. So we say that u0 is just always 1. So that is. So that's the whole model that we will solve. So it turned out that it's solvable. So what you can directly see is that this is essentially this second line is a symmetry of the equation. So if you change time by this factor, un by this another factor, and then you go through all this calculation, you see that alpha will cancel everywhere. So this is the system has this family of the scaling laws. So it's multi-scale system which has time scaling symmetry and space scaling symmetry, just like earlier equations. And with exactly the same conclusion. So whenever, if the solution will be statistically self-similar for given h, then zeta p will be hp. And if zeta p is nonlinear, it means that all symmetries are broken, but somehow the mixture of the solutions of the singularity with different h, if you follow this Parisi-Frisch idea. So let's see first why we took this complicated form of the equations, and in fact, you will these equations will tremendously simplify if we make a first transformation. Transformation to multipliers. And intrinsic times. So what we do is that we define what's called multiplier. So it will be W. It's UN divided by UN previous. So multiplier is normally a ratio between the amplitude of velocity at one scale divided by amplitude of velocity at another scale. But here we keep phase, so without modulus on the top, so it's complex. So this we will call it multiplier. And then we also want to define intrinsic scale, because what is intrinsic time? So the change of time at given scale is defined by the velocity at that scale or the scale at nearby shell. And now, so essentially we want to consider dimensional time, which is dimensionalized with respect to scale n. And the way to do it is you take kn, un minus 1 of t dt. So you see this is dimensionless quantity because this is wave number, so it's 1 over length. This is length divided by time and multiplied by time. So this is dimensionless quantity. So we define the intrinsic time by dimensionalizing the time with respect to the quantities at the scale n or nearby n. So this is intrinsic time. So these are new variables. So you can, given the un's as a function of time t, you can write wn as a function of tau n. So there is this transformation from u to multiplies intrinsic times, and there is an inverse transformation. The inverse relation gives you that, you see, inverse relation, it exists because W1 will be U1, because the denominator is 1 because of the boundary condition. So since W1 is U1, through multiplication of multipliers, you can reconstruct Un. So you can just check that Un will be just Wn by the Wn minus 1, Wn minus 2, and so on, W1. So this is a formula, or you can write it as Wn by the product n from 1 to n minus 1, Wn. So that's why W is called multiplier, because when you reconstruct N, you just multiply them. So this is inverse relation. And now what I want to express equation for this variable write equation of motion for this variable with respect to this time. I will not give you the full detailed derivation, but I'll give you the main step that you can just check. So how you do? So first of all, what is d tau n, you can substitute this second formula. So it will be 1 over kn, un minus 1, right? And then it will be d dt. So this is d tau n. And now instead of Wn, we put this expression. Un over un minus 1. Okay. I just substituted the definitions for each of them. The next is that we open up derivative. So when you differentiate the numerator, you get 1 over kn modulo minus 1 squared dun dt. And the second term will be minus what I want to put is this. Okay, so it will be un over kn un minus 1 cube d modulus un minus 1 dt. Okay. So the next equality. So now remember that un minus 1 modulus is square root of un minus 1 complex conjugated times un minus 1. So now you can differentiate this expression. So first time I will just copy. And the second term will become, so whenever you substitute and differentiate, you should obtain something like un minus 1, 4. And then there will be a real part of the un minus 1 star. Star is complex conjugation by dun minus 1 dt. So check this formula. So whenever you open this differentiation with expression, this is what you get. And now, substitute equations of motion. Equations of motion for dun dt and dun minus 1 dt. So these two equations we have. These two equations is what exactly this formula. So you substitute, and then you get a branch of terms. And then if you do this, which I suggest you to check yourself, it turned out that all terms will cancel, except for just one term. So everything will cancel. And what will be left? So this is the left-hand side. And what will be left from here is just this function. And this function is a function of, you see, of multiplier exactly. So somehow it's a miracle, but that's a miracle of constructing a equation in such a way that it happens. So what we get is that we obtain a system of decoupled equations. But each in its own time. So you see that all equations are decoupled. So for each n is the same equation, and they are not coupled. So there is no double n minus 1, there is no double n plus 1. It's just decoupled equations, but each in own time, and times are coupled. So why times are coupled? Because you see, if you take this equation, so what you can see is that d tau n plus 1 will be, so let's show that times are coupled. D tau n plus 1 will be k n plus 1 times modulo un dt. So plus 1 you can take 2 out. Then you can put un divided by un minus 1. Then what is left is kn modulo un minus 1 dt. And this is tau n, right? So this is, and this is multiply. So you see that there is a nonlinear, so there is this relation between the two next times, and then if you continue this to doing this, d tau n plus m will be to m, and then it will be product wn until w. Is it correct? Wn plus, it looks to be correct, plus m minus 1. So you see that there is a nonlinear relation between the times. So the equations are decoupled. Each equation evolves independently of the other, but times, all times tau 1, tau 2, at all times at the different scale, they are coupled through the solutions. So there is this interesting decoupling process that equations do decouple, but there is a sequence of time. So each solution at each scale lives independently, but with respect to each own time. And there is a complicated relations between the times which are solution dependent. So now we will see that these two properties will directly lead us to the intermittency after the break. So see you in 10 minutes. let's continue. So now, as we have equations, we can solve them, because it turns out it's not so difficult to solve them. Because we have an explicit expression for f. So for this f, the equation can be solved. That's a reason to choose that specific f, is that it gives a specific explicit solution. So something is, everything is adjusted for the solvability, but there is a strongly non-trivial part, is intermittency. So intermittency will come out. Okay, so what we do? So having this equation, we now split. So W is complex. So now we take represent it in polar coordinates. So it's mod absolute value and phase. And just check that. Check that if you split real part, so you check more absolute value and the phase. So what you get is that, so the general expression is like this: d rho n d tau n. In general, for this f, it can be expressed as real part from minus phase f. Okay. And now if you substitute f from what we have here, so you see we just need to put this specific f, and the minus e theta n will cancel this e theta, right? So, so the real part will be just the first three terms. So it will be r theta n plus dr theta n d theta n minus rho. So this will be first equation. And the equation for the phase, the general expression is given by imaginary part. So in the top we have something similar, is the same expression. And it's still divided by the absolute value. So what you do, exactly the same expression. So you get imaginary part will be rho, and you divide by rho. So it's 1. It's 1. So we get this system of equation, which we obviously can solve because second equation is derivative is 1. So from the second equation, theta n as a function of tau n is found explicitly. So it's initial condition plus tau n. And then what we do for the first equation, so you see this equation, this is an equation which has a autonomous part, the linear part, d rho n equal minus rho n, and the part which is does not depend on rho n, the non-autonomous part, and there is standard way how to solve it. So I'll just directly give you the answer, and you can check that it's. So first, without this term, the solution would be arbitrary constant Rn by exponent minus tau n. So this is a solution without these two terms. And then in order to take into account this term, we just add R theta n. So you can check that by differentiating this, R from here will cancel the first, and R from here will cancel the second. So these two terms cancel. That's it. So from initial condition, you can check that Rn is what? Rn is rho n 0 moment minus r at theta n at initial moment. So we have explicit solution, and this now putting this back to the formula, we give a general solution. General solution, which is equal in terms of initial conditions explicitly. So you get solution. So given initial condition, you know the solution for all times. I think I don't need any more of this. Yeah, this I don't need anymore. So one of the properties is, what you can see is that the observation is that each solution is bounded at all times by the two constants, which are both positive. So this small c and then another big C for some Cn and Cn. So there is some work to show that it's true, but what you can see is that you see, for example, how you find the bound from above. So this exponent is just gives 1, right? And then the first term is decaying, so it's not bigger than, it's always not bigger than Rn. And the second term is not bigger than the maximum of the function r, but function r is on a circle, so it has a maximum. So, for example, you can choose Cn as Rn plus maximum over the circle of R, right? And there is a little bit more work to show that also you can always choose also the lower bound. Of course, they both depend on initial condition, but given initial condition, for all times you have lower and upper bounds. And in particular, because of this relation, you see, since since Wn first of all, since Wn is bounded, we'll also have all Un are bounded, right? Because they're product. So all Un are bounded at both sides, and this means that there is a bounded rate for the growth of each intrinsic time. So in particular, all intrinsic times go to infinity as time goes to infinity. So this means that actually with this formula we just solved. We showed that there is that our shell model has a unique solution at all times. So the first theorem that directly follows from what we did is that for any initial condition, any initial condition. So this should be initial condition for which this representation is valid, and this representation is valid, it implies that none of them is 0. So one initial condition such that all un at 0 not 0 for all n there exists a unique solution. At all times. So we have global regularity. So this is global regularity. It's one of the things which is, as you remember, is always a trouble for the fluid dynamical modulus because it's of infinite dimension. So here there is no problem of global regularity. We don't even need to make a regularization. So this problem is made such a way that it's already good. So it can be uniquely solved for all times. So there's no problem at all. And each unt has global upper positive upper and lower bounds. What we just showed here. So solution is defined for all times, and each of them is bounded by absolute value. So each un just oscillates without passing through 0, but it's okay because it's complex, so it doesn't have to pass through 0. And define everywhere. So this is the first part, at least, which tells us that solution is defined for all time. So we can now compute structure functions. And let's do this. I will start here because I need this expression still. So the second part is really intermittency. So we now want to compute structure functions, and structure functions correspond to the time averaging. So we're interested in the situation as time goes to infinity. As time goes to infinity, we know that all intrinsic times goes to infinity. And what happens with the solution is that the first term exponentially decays and the rest will stay. Yeah, so in this limit, at large times, the first term disappears, all the rest remains. So there is an asymptotic form of all the solutions. So it approaches R at theta n, ei theta n, where theta n is this it's just linear function proportional to theta, to time. Okay, good. And then we can see that un, right? So un, which can be reproduced through absolute values, and we don't need un, we need modulo of un, right? So modulo of un, it can be written through the product of all modulus of Wn, Wm. And each of the modulus is just R. It's product theta n m. Okay. So we found our absolute value of the velocity for these phases, and now it remains to find what is the behavior of the phases. And we will write equation of motion for these phases. So d theta n d dt. So what it is, just use this formula. So it's the same as, so constant doesn't matter, so it's the same as d tau n dt. From the definition, it's kn modulo un minus 1. And again, using this formula, we can write kn by the product from m equal 1 to n minus 1 of this r theta n. So we have a closed system of equations, but coupled equations for theta n. So the coupled system for theta n. Because you see this is product from m to n minus 1. So each next n is obtained in terms of the previous ones. So it's a system. So theta 3 is obtained as in terms of theta 1 and theta 2. So this can be, and this system can be solved by explicit transformation. So consider new phases. So we call them alpha n, and it will be just theta n plus some function. So you see, each one depends on the previous. So we will correct the phase by some function of the previous ones. And we define this function in such a way so that this will simplify. So essentially there is explicit transformation, so it's hn. So it's for each n is different transformation. So hn is defined as, there is formula. So important is that there is a formula. It's explicit formula. You can see the explicit formula. So for in terms of where R0 is just mean value of this function R. So it's 1 over 2 pi integral from 0 to 2 pi r theta d theta. So we just give as this transformation in terms of the sum of the integrals of this function R. Just actually this transformation was not cooked. It appears by itself somehow. And then what you can check is that if you make this transformation, then and write equations for alpha, so what you get equations for alpha n as function of t. So you can check. There are more details in the paper, but essentially it's a direct computation. So you take derivative of alpha n with respect to time, and then it's the derivative of theta n with respect to time, which you know, and then there is this derivative of this expression, which is given explicitly. So you make manipulations which are elementary and find that it becomes tremendously simple. N minus 1. For all n. So somehow we not only decoupled this system, but we even made it the right-hand side to be constant. So right-hand side is just constant for all alpha, but with different constants. And now you must remember that alpha is a phase. It's up to 2 pi. So this is a constant speed, how it moves along the circle. So all of the phases move along the circle with different phases. So for example, so the phases, and you can take just any finite number of these phases up to n. Let's take it up to small n, up to n. They rotate with speeds. Rotate because it's along the circle, so every alpha n is on the circle, with the speeds which are first rotates with k1, just k1, second k1, k2 r0, then next k3 r0 square until kn r0 n minus 1. So there are a sequence of speeds with which all of them rotate. And important is to take the speeds different in such a way that each of the phases rotate essentially not in a resonance with any other. And how you do this? So these speeds, so if R0 is transcendental number, remember what's transcendental number, so it's then you see these are powers of the same number. So if R0 is transcendental, then no combination of these numbers with integer coefficients gives 0. Because transcendental number is not a solution of any polynomial equation. So that means that all of them are rationally independent. So there cannot be any resonance between them. So then speeds are rationally independent. Speeds are rationally independent, and then there is a theorem which tells that whenever you have angles rotating with rationally independent speeds, the system is uniquely, what's called uniquely ergodic. Then the system for alpha 1, alpha n is uniquely ergodic. And this implies one very important consequence, that the temporal average, so average in time for any function of these variables is the same as the average in space. And average in space means that we also should divide by the volume. For any function, at least continuous function of this variable. So any function that you take, the system nuclear logic means that any function that you take, it doesn't matter if you average it in time or you just integrate with respect to variables. So it means that each solution will go through all the area, nearby every point, and it will somehow visit all the space uniformly. So it will visit every point in the space uniformly. So it means that whenever you make average with respect to time, it's the same as just average with respect to space. So this is what we know from dynamical systems. And then very little left. So next, what you should take into account that we had alpha n as a transformation of theta n with this transformation. But determinant of this transformation, so you see this is theta, alpha n is theta n plus function of the previous ones, which means that the determinant Jacobian of this transformation is 1, right? Because Jacobian will be diagonal matrix with diagonal 1. So since the transformation from theta 1, theta n to alpha 1, alpha n had Jacobian determinant equal 1. It means that instead of, it doesn't matter if you integrate the function with respect to alpha or theta, the same thing. Because transformation gives a determinant of the transformation the same. So the average in time is the same as 1 over 2 pi n integral f theta 1 theta n. And now what's left is to take right function f. So now we take f to be un p, which is, as we remember, is this product. Just put it taking power p from each term. So the first term will be just structure function. This is by definition. So this is temporal average of u and p. And the right-hand side will be integral. So it will be 1 over 2 pi n integral of this product p theta m d theta 1 d theta n. But now the integral completely couples for each. Theta 1 integrates the term with m equal 1, theta 2 integrates the term with m2, and so on. So this can be just factorized. And each term is the same. So now each term in this product will be just integral from r, p of theta, d theta, because for every m will be this integral. And it will appear n times here. We have prefactor n times, so this power n. Okay. And this is, so let's call this term to be 2 minus zeta p. So if it's 2 minus zeta p, it becomes 2 minus n zeta p. And this is L zeta p. So what we get? What we get is all structure functions are exactly, now not even asymptotically as in a usual turbulence, but exactly power laws with a coefficient 1. We even compute coefficient, where zeta p is minus log 2, so we have to minus log 2 of this expression. Of the moment of the function r. So that's it. And this is second theorem. So second theorem tells us that whenever for any solution from the theorem 1, every solution gives us structure functions which scale as a power law with zeta p given by this expression. And this expression is usually nonlinear. Generally nonlinear in P, which means that system is intermittent. So that works. So now I want to show some simulations which just confirm that we have to turn it on, no? Funzionando, no? Where is it? So what you can see, so essentially what we can do, we take specific function R. Is it visible? No, it's not. Works. Funziona. So we take specific function R, and for this function you can it takes this formula that we had and compute explicitly the zeta p in terms of just to take an integration, and you will see that your dependence of exponents with respect to p will be nonlinear. So this first graph on the left here, so it will be nonlinear. And then you can numerically compute structure functions as a function of n. And using this logarithmic scale, you will see that they are power laws. And so here the point is a vice versa. So points is a numerical computation, and the straight lines is a theoretical value given by the theorem. So you see everything works. And now we can see what means intermittency. So this picture on the top shows the usual evolution of all absolute values of all velocities. So you see that first velocities, it oscillates slowly. Then the second U2, it oscillates slightly faster. Then U3, it oscillates slightly faster again, and so on. And smaller scales you go, they oscillate faster, but not only faster, they oscillate in a more singular way. So because intermittency is not just oscillation, speed of oscillation, but intermittency means that it should incorporate different type of scalings at the same solution. So whenever you go to smaller scales like U10, so the scale which is 1,000 times more or less smaller, you see the oscillation become really intermittent. So there is an area where it oscillates very strongly, then oscillates in a medium way, then almost doesn't oscillate at all. And then again oscillates strongly. So it's a combination of different types of singularities put together in one solution. So whenever you go even smaller scale, you see it become stronger and stronger. So this is what intermittency means, and this is exactly the way how you can how we obtain intermittent solutions with these structure functions, which all have different nonlinear. The powers has a nonlinear dependence on p. So that equation, at least we have one example which completely reproduces the scale, this picture of intermittency in solvable model. So the last thing I would like to discuss, which will be introduction to the topic, which I could not even touch. I wanted, but we really don't have time to do this, because this would be a rather large topic. Is about hidden symmetry. So it has to do with, in relation to the example we have, it will have to do with the question why it worked. So why we succeeded to solve it and reproduce intermittency in example. So what specific is in this example which makes it intermittent and solvable? And this has to do with much wider notion about hidden symmetry. And I will only display the symmetry for this equation, and then for who is interested to learn more, I can send references. So in order to see what is a hidden symmetry, we have to consider the relation between original system and the system in these intrinsic time variables. So we have original equations. So original equations was this dun dt equal something, and which were all coupled. And then we had uncoupled system of rescaled equations for multipliers. So this was coupled. This became uncoupled. This has just made it solvable. But making it solvable doesn't mean that automatically that it will be intermittent or there will be any power loss. So why power loss appear? And power loss appear is because of this restoration of the symmetry. So remember that what we already discussed is that intermittency has to do with breaking the scaling symmetries. So we had scaling symmetries. Scaling symmetries in the original equation. And these are TUN, substituting TUN by the new time and new variable, where alpha was 2 minus m. So these were scaling symmetries, and they are all broken by our solution. So all scaling symmetries are broken, which is automatically implied by the intermittency. So the nonlinear dependence of zeta p on p automatically implies that there will be no one of the symmetries is true, is a symmetry of our solutions, even in the statistical way. But this equation thus has a different scaling symmetry. So the new hidden scaling symmetry. And this symmetry is in terms of this equation is very trivial. So you can take tau n wn and substitute by tau n plus m w n plus m for any m. So if you change this by this, it's the same equation. Equations do not change because they do not depend on n at all. So this symmetry is restored. So actually, there is a restoration of some symmetry. Despite all symmetries are broken in the original system, there is a symmetry for the rescaled equation, which is restored. And the restoration of this symmetry is exactly the reason why power laws of structure functions appear. And essentially, this is a result, or this is the symmetry implies that all structure functions, they scale as power laws. But since the symmetry is weaker, it does not imply that powers are linear functions. Powers, zeta p can be arbitrary function. So each of these symmetry would imply that zeta p is a linear function of p. And this symmetry implies that just there is a power law, but zeta p is some function. And so there is this restoration of hidden symmetry. And you should not think that this is a simple symmetry, because I already showed that this is actually, it looks simple in terms of taus when you consider different times. But in fact, the transformation from tau n to tau n plus m is a complicated nonlinear transformation. Remember, I wrote a formula for this. So this is actually this transformation, unlike this symmetry, which is just linear change of variables, this is a rather complex nonlinear transformation of equations, in fact. So that hidden symmetry is something more complex. So the question whether this mechanism can be generalized, it turns out that this symmetry extends to other systems as well, in particular to the Navier-Stokes Euler system. But this is already goes far beyond our lecture. So I will finalize. So this is today is a final lecture. Now I want to give you some exercise. So it will be project free. Take a different function r theta and compute numerically or analytically, if you can, zeta p for, let's say, p equal 1, 2, 3, 4, compare with numerical simulations. For details, you can check the paper. So what I said, that it's a paper that you can take in my web page. So this is the paper of 2021 in the communication and mathematical physics. So just make this numerical analysis, but for different R. And why I'm giving this project, so there are, I gave through the course of lectures 3 projects. The one was about blow up. The second was about regularization of singular system. And the third about this intermittency. So who wants to get a note for the course should make 3 projects. So it should be one of these 3 items. So project 1, project 2, project 3, or a presentation. So for who gave a presentation counts as 1. So you have to do at least 2 projects out of 3. If you want to have a note. Okay, if you don't want to have a note, I can give there is also a way P that we put for those who didn't get note. But I think that making these 3 projects, which are on one side they're elementary, on the other side they're not simple. So it gives you a very good idea what happens in real equations, not just by studying theory, but really looking what is the mechanism of this phenomenon. Blow up, regularization, vanishing regularization, or intermittency. So really, I suggest to do it. So today's last lecture. Still, if someone have questions, especially about projects, you can write me an email, and we can probably set up some online meeting during these hours of tomorrow lecture, the day after tomorrow. So if someone wants to discuss, they're very welcome. So thank you and goodbye. So till next time.